Welcome, everyone. Congratulations. If you are here, you have made it to the final day of AAS 245 for National Harbor. It is Thursday, January 16th at 2:15 p.m., and we are gathered for the last press conference of this session, which is titled Galactic Histories and Policy Futures. My name is Susanna Kohler. I'm the press officer of the AAS, and I am assisted today by Carrie Hensley, the deputy press officer of AAS, and Lexi Galt, who is the AAS Media Fellow and a graduate student at Indiana University. And we are very excited to bring you this mishmash of topics in today's session. We have 3 talks that are on some of the latest results in galaxies. And then we have a 4th speaker who's joining us from online, who's going to discuss some policy topics. So I'm going to go ahead and run through just a few notes first. If you have any cell phones or anything else that might make noise, please make sure those are silenced before we get going. Note that this is being recorded. This session is being live streamed to YouTube as well. And we're going to have that video archived after this, so that will be available to you if that is something you want to reference later or view later. All of the recordings from our briefings will be added to the press kit, as well as any press releases, media advisories, etc., related to that, and the slides from our presenters. And those are all in the press kit, which is accessible through the meeting website, the AAS 245 meeting website. There's a section specifically for press, and the press kit is linked there. You can also find it in the press conferences channel of the Slack. So for anyone who has not been to a AAS press conference before, the way this will work is that we're going to go through, I'm going to give a brief introduction to our speakers today, and then we're going to go through and have all of the presentations back to back in turn. We ask you to hold your questions during that time until the very end, and then we'll move into a joint Q&A session for everyone. And for folks in the room, you can ask your questions out loud. We'll have a handheld mic that we'll bring around to you. For folks online, you can queue up your questions at any time via the Zoom Q&A box. We ask that when you type your question in, you also identify yourself and your affiliation and who your question is for. So, all of that said, let's get going. Our first speaker today is going to be Catherine Fielder from University of Arizona, who's speaking on a dwarf galaxy stellar halo built by accretion. Then Kristen McQuinn from Space Telescope Science Institute and Rutgers University will talk about the boundary of galaxy formation, constraints from the ancient star formation of the isolated, extremely low mass galaxy Leo P. Then Zhuo Chen from University of Washington will present on resolving 90 million stars in the southern half of Andromeda. And last up, John Barentine, who's joining us online from Dark Sky Consulting, will present on some recent space policy statements regarding our dark and quiet skies. So I'm going to take a minute here to set up the Zoom correctly. And I will turn it over to Catherine.
All right. Good afternoon, everyone. So I'm here to show you a rare, unique, and one of the first glimpses at looking how a very small dwarf galaxy is evolving and how it gives us insight into the very small details of galaxy evolution. This is a big effort, in part at the University of Arizona, as well as with the Delve collaboration, which I'll expand upon in a moment. So before I can get into the really exciting results, I want to provide you a little bit of context. So massive galaxies like the Milky Way or more massive grow hierarchically. This is a term that astronomers like to use that really means small galaxies coming together over billions of years to form larger and larger galaxies. And so this is our picture of hierarchical assembly. We know this very well at mass scales like the Milky Way or more massive, because this process leaves behind signatures that are in the form of streams and shells. There are these distinct features that you can see around these other Milky Way mass galaxy images here, as well as some other accreted stars left over from old dwarf galaxies that have been destroyed. And this conglomeration of streams and structures and stars that are well beyond the actual disk of the galaxy, we refer to as a stellar halo. So this is well understood for massive galaxies. But what about dwarf galaxies? Like one of our companions, the Large Magellanic Cloud, is a very well-known dwarf galaxy. So dwarf galaxies, unlike something like the Milky Way, have much fewer opportunities to assimilate even lower mass systems, right? Because dwarf galaxies have a weaker gravitational potential than something like the Milky Way. And so understanding exactly how dwarf galaxies grow over time remains a bit of an open question. It has been posed previously, do dwarf galaxies even contain stellar halos? If so, how do these stellar halos form? As I mentioned, they have fewer opportunities to maybe assimilate very low mass galaxies. And then there are other processes that dwarf galaxies are much more susceptible to, such as stars blowing up in supernova can displace stars very far out from the disk. And perhaps this is another mechanism to form a stellar halo in a dwarf. I also want to emphasize we want to look for isolated dwarf mass galaxies to really answer this question. This here is an image of the local group, which you can see is very busy. The Large and Small Magellanic Clouds, in addition to all the other dwarf galaxy companions the Milky Way has, are subject to very intense tidal forces imparted onto them by the Milky Way. So it's difficult to disentangle the different effects happening in these dwarf galaxies very close to us. And this is where the Delve survey comes in. This stands for the DCAM Local Volume Explorer Survey, which is a comprehensive program aimed at imaging the entire southern sky with the Blanco 4-meter telescope at the Cerro Tololo Observatory in Chile. Delve Deep specifically has focused on very deep imaging around a few different large and small Magellanic Cloud mass dwarf galaxies. So just to give you a sense, here's a very pretty image of NGC 300, which is the galaxy I'm talking about today. You can see it very clearly. And after the Delve Deep data, you can see we have a very extensive view around this galaxy, all the way out to the approximate edge of its gravitational influence. Now, this might look a little different than the pretty picture that you're seeing, and that's because this is actually individual stars that I'm looking at. So the goal here is the streams around a dwarf galaxy will be so faint that we actually can't see them in a regular image like you see on the left. So I actually need to look at individual stars causing overdensities to actually look for structures. And you might already see, oh, it looks like there's something happening around it. So just a little context for NGC 300. It's very similar in mass to Large Magellanic Cloud, and for comparison, the mass in stars is about only 5% that of the Milky Way. It's much smaller. It lies at the edge of the Sculptor group, which is 6.5 million light years away, but it's quite isolated. Historically, NGC 300 has actually been a well-known example of a very normal, regular, maybe boring galaxy. And now with our new survey, we've been able to see that maybe that's not the case after all. And just to highlight to Dave Sand's talk yesterday, it might also have some smaller companion dwarf galaxies. So now this is the really big exciting result where the resolved star maps reveal a wealth of structure around NGC 300. So on the right, you're still looking at that star map. And then on the left, you're seeing just a smooth version. So it's a little bit easier for you to see the different structures. So there's this very extensive stellar stream you can see extending from the north. It actually extends more than 100,000 light years from the center of the galaxy, which is close in size to the diameter of the Milky Way itself. So this is a very large stream. You can also see some other structures. You can imagine these two little shell features. It's kind of like when a dwarf galaxy is hitting this more massive galaxy, it's causing a ripple, and that's what could cause those shells. And then this stream S that you see, this southern part of a stream, could be a potential part of a stream wrap where the galaxy falling in turned around in its orbit. And so a stream like this is very likely to not have originated from the galaxy itself because of how large it is. Another way to try to understand, are these really coming from a different galaxy or from NGC 300 itself, is to look at something called metallicity. So astronomers use this term to refer to just the amount of heavy elements within the material. So a higher metallicity in a galaxy means more generations of stars have lived to further enrich the gas within it. So you can imagine in a galaxy like NGC 300, the disk itself is relatively metal rich because it's had many eras of star formation. Lower metallicity is referring to older or less processed materials. And so the smallest dwarf galaxies that even another dwarf galaxy could pull in would be the most metal poor because they have had fewer material in order to enrich their own gas. And so you can see in the top versus bottom column, I have labeled metal poor versus metal rich things. And you can see these streams, this shell structure still very clearly in this metal poor resolved stellar map that really aren't present in the metal rich map. And so that really is telling us these structures likely originated from a tiny galaxy that NGC 300 has since pulled apart, and now we're only seeing these very faint remnants of this old interaction. So to tie this all together, the stellar halo of NGC 300, its outskirts well beyond the disk, seems to be built by accretion in the sense it's pulled something in, and thus now it's building up its own system. In fact, this is the richest structure ever seen around a galaxy of the mass of the Magellanic Clouds or smaller. And so it's really telling us even dwarf galaxies can build stellar halos through accretion of smaller galaxies, kind of similar to the growth pattern that we're seeing in very massive galaxies. So now NGC 300 is this very striking example of accretion-driven stellar halo assembly in a dwarf galaxy, giving us better insight into how the smallest galaxies form and evolve. I want to emphasize we have an additional sample of other galaxies to look at, so this is really just the beginning. This is all preliminary science for when we have our next generation of surveys with Rubin, Roman, and Euclid. And we're really standing at this precipice to understand how the smallest galaxies have formed and evolved over time. Thank you.
I'm Kristen McQuinn from the Space Telescope Science Institute and Rutgers University. Our team has studied this really small galaxy named Leo P. Shown here in the image on the right, taken with JWST, are these blue points, which is the population of stars within the small galaxy Leo P. Leo P is located just outside our neighborhood of galaxies, and it's quite small, and because of its low mass, it makes it really interesting to study. Through the stars, the stellar measurements we took with the JWST data, we found a surprising trend in its history. Leo P started making stars early in the universe and then stopped for billions of years. It had a period of quiescence before reigniting and continuing to make stars into the present day. Little galaxies are really interesting because they are sensitive probes of environmental factors. Leo P has about 20,000 times the mass of the sun in stars, which is about 1 million times smaller than a massive spiral galaxy. Shown here is the approximate physical scale of Leo P on the left compared to a local spiral galaxy. So Leo P is essentially the size of a star cluster. And these little galaxies are interesting because they are so sensitive to environmental effects, and we can connect them, for example, to conditions in the very early universe when structure was first forming. The graphic that I'm showing here is a history of the universe. From left to right, left is the Big Bang, and right is the present-day universe. And as we move through the dark ages, and the first galaxies were forming, they had massive stars that produced copious amounts of UV photons that permeated the universe. These UV photons ionized the gas around the galaxies, which you can see in these grayish kind of circles. And as time went on, these ionized bubbles grew and merged until we find ourselves in a predominantly ionized universe today. So in this epoch of reionization, you can imagine taking a very small galaxy and locating it in or around one of these ionized bubbles. The heat from this UV, the bath of UV photons, will heat the gas inside little galaxies and puff it up. Combined with stellar feedback and supernova inside a galaxy, you can imagine that star formation can just shut down. It's really hard to make stars from hot gas. And so theoretically, we think that little galaxies like Leo P should have started making stars early in the universe and then should be quenched. Some of this depends on where the galaxy might have been located. If it's located inside one of these ionized bubbles at early times, it might have been more impacted at an earlier time than, say, if it was located outside of one of these bubbles at earlier time and grew a little bit more. But regardless of the exact location, our theories suggest that these should be quenched. And observationally, when we look at galaxies in this mass regime, we do find that that's the case, except the galaxies that we've studied have almost all been around the Milky Way or Andromeda. So shown here is a graphic of the Milky Way galaxy surrounded by its satellites of little galaxies. And the galaxies for which we have the requisite data, when we measure it, indeed, it shows they've made stars early and then nothing else. And our interpretation is that reionization has been the culprit. Yet these galaxies are the neighbors of a behemoth massive galaxy. They're subjected to ram pressure stripping and tidal interactions, and it's difficult to unambiguously separate the impact of reionization from these other complicated environmental effects. And so Leo P offers us an opportunity to disentangle these impacts. Leo P is extremely isolated. It's more than 5 million light years away from the Milky Way. And this isolation factor just allows us to disentangle the different environmental effects. So we targeted this with JWST in cycle 1, and we imaged the galaxy. With the resolution of JWST, we've been able to resolve the individual stars in the galaxy. We had previously imaged this with Hubble, and Hubble's also able to image the stars. But with JWST's larger mirror, we were able to be sensitive to fainter and critically older stars. And so when you measure from an image like this, the brightness and color of stars, you can approximately age date the stellar population. You can go on an archaeological dig and find the oldest stars in this galaxy that were formed at the dawn of the universe. You can also age date the stars at intermediate times, and you can identify the stars that were formed relatively recently. So you can put all that together to create a plot of the birth rate of stars or star formation history, shown here. On the y-axis is the fraction of stars made, and on the x-axis is the function of time. So if we look at the very early epochs of time, Leo P made almost 20% of its stars, shown here. And then after the epoch of reionization, the galaxy got really quiet. It stopped making stars for billions of years. And then for some reason, it reignited star formation and continues to make stars at the present day. So this is a little unexpected because of its mass regime. We would have expected it to be completely quenched. But the pattern of early star formation, quiescence, and reignition allows us to test some of these theories more concretely. But Leo P is just one galaxy. So we probed the archive to see if we can find other data archives, to see if we can find other galaxies that are isolated, low mass, with the requisite data. We found 3 other similarly low mass galaxies, and their results are intriguingly similar. All 3 of these systems show early star formation, followed by an extended pause, followed by reignition of star formation. And interestingly, these galaxies span a range of masses. Leo P is the smallest of the 3, 2 of them about a factor of 10 more massive, and 1 of them is more than 100 times more massive than Leo P. So there's some really interesting implications from these findings. The first is that reionization may halt star formation in galaxies more massive than these small ultra-faint dwarfs. There's a mass threshold above which we really didn't think reionization was impacting galaxies, and these 4 systems are suggesting otherwise. In addition, the impact of reionization may be environmentally dependent. So these 4 galaxies all being isolated and showing some signs of impact by reionization, but also reignition, suggests that maybe reionization, they're finding the impacts of it a little bit later in time in the universe. So that wave of reionizing photons didn't strike them until they were just a little bit more mature and a little bit more massive and able to retain their gas and form stars longer. So that's an interesting takeaway from this. The cause of reionization remains an open question. There are a number of different ideas of why these little galaxies reignited, but they're all still preliminary interpretations. And finally, one of the more nuanced conclusions of this is that if the trend continues, if we get more data on galaxies like this, and we see this extended pause in star formation from a redshift of 5 to 1, which is a significant fraction of the age of the universe, then it would suggest that low-mass galaxies are pretty quiet for a good chunk of time. That means they're also not making massive stars or producing UV photons, which has interesting implications for the UV galaxy luminosity function at faint magnitudes. We have an additional 4 galaxies in the works to be able to double our sample to see if this really interesting trend continues. Thank you.
Hello, everyone. My name is Zhuo Chen from University of Washington. Today, I will be sharing the Treasury program we finished last year, the Panchromatic Hubble Andromeda Southern Treasury, to resolve over 90 million stars in the entire southern half of M31. The local group is the closest example or laboratory for studying the physics and astrophysics that controls the formation and evolution of galaxies in the universe. M31 is the closest large spiral galaxy to our Milky Way. Andromeda is like the Milky Way, but a lot easier to see. This is like trying to understand the layout of New York City when standing in the middle of the Central Park. It's always hard, right? And studying M31 circumvents such complications like line of sight reddening, the uncertain distances, the background or foreground confusions, and also allows the further studies on the context of M31's local environment. HST is capable of resolving thousands, hundreds of millions of stars in the local group. And roughly 10 years ago, the Panchromatic Hubble Andromeda Treasury Survey successfully mapped the northern half of Andromeda. And you can see this is the fat mosaic revealing over 100 million stars and thousands of star clusters. So Hubble is powerful enough to resolve individual stars there. It's like photographing a beach and resolving individual grains of sand. And the FAT program covered 6 filters ranging from the near UV to near IR. The galaxy is so large and so close to us with the angular size around 6 times apparent diameter of the full moon. So it took actually more than 12,000 images at 414 positions over 39 months to make this happen. And now we have created a similar legacy map on the southern half of Andromeda in this Panchromatic Hubble Andromeda Southern Treasury Survey, covering out to around 13 kpc along the southern major axis. So now the big difference in this FAT survey is that we don't take infrared data. So we only require around 25% of the FAT time to cover both UV and optical in 4 filters. The near infrared can be added later with a very small amount of observing time using Roman Space Telescope or Euclid for a high efficiency. And then the zooming panel there just shows the overall exposure map of the entire survey. So with the 2 Hubble programs, now I want to show this. We obtained the really, really cool photo mosaic of the entire disk of M31. This stunning, colorful mosaic captures the light from over 0.2 billion stars in optical. And this is the largest, sharpest HST mosaic ever made from the observation spanning more than a decade with tons of effort and support from everyone in the collaboration FAT-O-FAST. And it's also very challenging to actually stitch together all of this more than 600 Hubble overlapping snapshots. So this ambitious photography actually represents a new benchmark for precision studies of large spiral galaxies. And then this is the very first time that we can see such detailed structures from for an external spiral galaxy over such a large and contiguous area. And earlier, one big question was like, why we need to spend so much time again just mapping the other half of the galaxy, right? And now you can see the asymmetry between the two halves are now visually evident in the figures on the slide, and more intense and varied structures in the south, along with some of the new information from the intersection with M32 and M31 disk, and split portion of the star-forming ring you can see on the bottom, and then further connecting all the way down to the giant southern rim. So the observations on the 1000 disk are just more sensitive to help us further constrain the merger and accretion history of M31. And now let me walk you through this incredible video, part of our Hubble's press release, to zoom in and show some of the rich details in different regions across the whole disk. So the camera first zooms into the central region of the galaxy, resolving older stars, showing the yellow and whitish colors. And then our view is kind of obscured by some of dark dust clouds, and you can see this very prominent dust lane across the entire southern disk. And now we're looking at the youngest stars, young stars associations in M31, the NGC 206, one of the largest and the brightest star-forming regions in the local group. And then keep going, the camera sees more young stellar clusters showing blue. So the brightness and colors of stars are just telling you like the formation and evolutionary histories of the entire disk. And then the stellar population looks a little bluer as we move toward the outer region of the galaxy. And then finally, the camera pans on the satellite galaxy M32, the big blob there, mostly old faint stars with no most recent star formation. So besides the cool mosaic and video, for science, we have measured good quality photometry for more than 90 million stars in the 1000 disk of Andromeda. And this figure on the slide is showing the color magnitude diagram for stars in the optical, with the x-axis showing the color, y-axis showing the brightness. And you can see the prominent features on CMD can also help us select broad populations into approximately 4 age bands. And then we can construct the stellar density maps for those populations respectively. So let's start from the full mosaic. If we only select old populations, like older than 2 billion years old, then it shows a relatively smoother density gradient, very typical to a disk galaxy. And then if we select relatively young populations from the disk, like we're able to see some more spiral armor structures. And here you can clearly see the split portion of the star forming ring on the left-hand side, like close to M32. And then if we only select the youngest population, younger than 200 million years old, and more pronounced spiral armor structures show up, but no stars in the center, like a central bulge area of the galaxy. So those are like really young stars for the very top stellar density map. And the younger populations here from our survey just directly trace and quantify the signatures of spiral arms in the disk for the very first time using the stellar populations directly. And then the detailed star formation history is being analyzed using the photometry catalog in detail. But this fantastic stellar density maps just show the glimpse with lower time resolution and highlighting the great potential of this catalog for in-depth studies on the star formation history. I think the main takeaway is this big mosaic. So I will stop here and take questions in the end. Thanks.
All right, I'm going to go ahead and switch us over to the other desktop. And John, if you want to go ahead and unmute yourself, make sure we can hear your audio in the room.
Okay, can you hear me?
We certainly can. Perfect.
All right. Okay, go ahead and share my screen.
Yeah, please do.
All right. Well, thank you. Now for something completely different. Today, I will tell you about some of the recent policy statements concerning dark and quiet skies that AAS has released. My name is John Barentine, and I represent the AAS Committee for the Protection of Astronomy and the Space Environment, or COMPAS for short. This is an advisory committee of the AAS Board of Trustees that represents the Society's interests relating to topics affecting the night sky, the space environment, and other influences on astronomical observations, both from the ground and from orbit. Our mission is to empower AAS members with information and resources so that they can themselves be more effective advocates for astronomy. And we have subcommittees that engage in all of the topics that are listed towards the end of this slide in the blue. COMPAS exists because the dark and radio quiet sky is under threat around the world. We routinely deal with issues that relate both to terrestrial sky glow, which is most commonly referred to as light pollution, interference with radio astronomy observations, and increasingly with the issue of the rapidly rising number of objects in orbit around our planet. In each of these broad realms, there is both an educational and an advocacy aspect to the work that we do. Although terrestrial interference to astronomical observations at optical and radio wavelengths remains at the core of our efforts, more and more we find that new and insidious challenges to astronomy are coming from space. In recent years, this has had to do with the rapid proliferation of large satellite constellations. But we are now also equally concerned about emerging technologies, such as plans to deliver solar electric power from space to the ground. As the cost of launching payloads has plummeted, we're equally mindful about the prospect of new activities in space, such as commercial advertising, that have the potential to negatively impact astronomical observations. With oversight from the AAS Board of Trustees and the Committee on Astronomy and Public Policy, COMPAS looks for opportunities to help shape the Society's positions on these various matters and to communicate those positions to policymakers and to the public. And then today, I want to draw your attention to a few of our recent actions in particular. In September 2024, we promoted and the AAS adopted a statement advocating for transparency in the way that spacecraft missions to deep space and cislunar space, or the space around the moon, are conducted. In particular, the request for transparency has to do with the locations of objects that are sent into these realms of space. Simply, we need to know where they're at. To quote the statement, such transparency is essential for promoting space situational awareness, reducing interference between missions, avoiding interference with observations of natural objects, including observations of potentially hazardous asteroids, and ensuring the peaceful exploration and use of outer space, including the moon and other celestial bodies. It calls on the United States to make licensing conditions that launching entities report publicly on the trajectories of their spacecraft using open standards, and to place information about trajectories into public repositories. To the extent that some of this information is sometimes restricted as a matter of national security, AAS believes that policymakers should reconsider this, as there are currently no reasons to believe that sensitive missions operate in these realms. Over time, the government should consider extending this idea into other parts of space, such as low Earth orbit. And for as much concern as there is about the operation of active spacecraft, the Society views with alarm potential impacts to our planet having to do with the disposal of spacecraft at the end of their missions. As a matter of reducing the risk of collisions to also reduce the generation of new space debris, in 2022, the U.S. Federal Communications Commission set a 5-year rule for the disposal of satellites through controlled deorbiting. We applauded that decision at the time. However, in September 2024, we noted our grave concern about the impacts of emissions and effects from extensive space launches and space object re-entries on Earth's sky and its upper atmosphere. Given the many unknowns concerning the deposition of materials such as black carbon soot and water vapor at middle altitudes due to rocket launches, and of metal atoms in the ionosphere during re-entry, the AAS recommends that regulators and policymakers seriously and substantively consider the issue of atmospheric pollution resulting from the full life cycle of activities in space. We urge federal regulators to observe the precautionary principle when writing rules governing these activities until the risks are better understood. And today we unveil a AAS statement on the issue of obtrusive space advertising as it may impact astronomical observations. This is a form of commercial advertising in space defined in US law as, quote, capable of being recognized by a human being on the surface of the Earth without the aid of a telescope or other technological device. There are reasons to believe that this activity will be pursued globally in the very near future, as shown by the 2024 launch of a Russian prototype CubeSat intended to demonstrate the feasibility of this technology. US federal law currently prohibits the launch of payloads containing material to be used for the purposes of obtrusive space advertising. Because this activity constitutes potentially harmful interference with ground-based astronomy, AAS urges world governments to follow the US example and prohibit obtrusive space advertising by appropriate international convention, treaty, or law. The Society also urges the US delegation to the United Nations Committee on the Peaceful Uses of Outer Space to support such a global prohibition. I also want to mention a couple of other actions taken by Compass in the last year that support our advocacy goals. AAS endorsed the Dark and Quiet Skies Act, introduced by US Senators Hickenlooper and Crapo, to establish and fund a National Institutes of Standards and Technology Center of Excellence to research mitigations for satellite impacts on observations. We contributed content to the International Astronomical Union Resolution 1, which calls on the IAU to formally include protecting dark and quiet skies as part of its overall mandate. And we provided a comment to the US State Department on proposed rulemaking having to do with loosening export control restrictions on information about satellite brightness mitigation efforts. All of these efforts are either linked on the AAS website or on the Compass website. And lastly, I would like to draw your attention to our committee's media contacts in all of the subject areas that are within our remit. Contact information for our subject matter experts is available on the Compass website. These folks can help comment on our work and provide technical expertise to inform stories on any of the issues. The link shown here leads to a number of useful resources for journalists, and we hope to hear from you. And so with that, I will hand it back over to Susanna.
Great, thank you so much. So I'm going to, let's see, I'm going to leave John on the screen here so that we can still see you in our Q&A session. But we'll go ahead and go into Q&A now. I will run the mic around myself. So again, if you could identify yourself and your affiliation when you ask your question and who your question is for, and same goes for the folks online. If you could do that when you queue up your questions, that would be great. Ethan.
All right. Thank you, everyone, for such really good talks. I have two questions, and my first one is for Kristen. Kristen, thank you for this. I'm really curious about this burst of star formation and then a long quiescent period and then more bursting and a little quiet. I noticed, like you pointed out, that that first, stoppage of star formation seems to happen right around the epoch of reionization, 500 to 600 million years after the Big Bang. But I was curious, was this galaxy more massive than an ultra-faint dwarf galaxy after 500 or 600 million years? Or did it possibly just quench from reionization like those ultra tiny galaxies do, and then gradually accrete enough mass over billions of years to finally trigger a new burst of star formation? Is that a plausible scenario?
You've definitely done your homework. Yes, that's absolutely a plausible scenario. And in that scenario, the difference between Leo P and a galaxy of similar mass in the early universe that was in a more complex environment is that Leo P, because it's isolated, could continue to accrete matter, having a bigger dark matter halo, a deeper potential, being able to accrete additional gas, whereas a similar type galaxy sitting in the hot halo of a Milky Way at early times, it's much more difficult to accrete gas and grow because of the ram pressure stripping and the tidal interactions and just the challenging of that environment. So that's exactly one of the plausible scenarios of what's happening to Leo P and the other galaxies like it.
Okay, thank you. My second question is for Catherine. Catherine, thank you for this very interesting talk about NGC 300 and its newly identified stellar stream and shells. And I'm really curious now, from the observations you've been able to take, can you say anything about the time scale for this merger that led to this remnant tail that we see? Can we estimate how long ago such a merger would have occurred based on the mass of NGC 300 and the properties of the remaining bit of the stream that we can still see?
Yeah, that's a great question and something we've also been thinking about. So this is something that is a bit contingent on now we need to look at models to really get a good grasp of how long ago did this merger occur. My intuition is that it is long enough ago that we really only see the signature in overdensities of stars instead of in diffuse light. But beyond that, it's definitely a bit hard to exactly say when. And this is something we definitely want to work towards understanding better.
Thank you. My question is for Zhuo Chen. Thank you for this beautiful use of the Hubble Space Telescope. My question is how this wonderful mosaic that covers the entire disk of M31 would fit scientifically or complement what we might be able to do with the Roman Space Telescope in the infrared, as it's designed to do these wide fields. So I know you've probably been thinking about that, but can you talk about the kind of complementarity between what we may be able to do with Roman with what you've done beautifully here with Hubble? Thank you.
Yeah, thanks for the great question. That's the stuff we have been thinking a lot about the infrared, because for FAST, for the time efficiency, we didn't do any of the infrared observations. And for Roman, it just needs like a one or two shot. And with infrared, it's crucial to know the infrared data because we need to identify the extinction map and the Asian star formation history and do the stellar SED feedings. All this kind of science require the infrared data that we're kind of struggling with if we only have the optical and UV. So that's definitely the plan with, I think, some of the potential of nearby galaxy survey using the Roman or Euclid to map the other half, definitely the other half of the galaxy. And if available, we can definitely take the whole as to know the systematics between different surveys. That's definitely a good point. Thanks.
Battling questions here. Martin Ratcliffe with Evans and Sutherland Planetarians for Kristen again on this wonderful dwarf galaxy thing. Do you have any estimates of after the epoch of reionization, how much kind of interstellar gas is left in that galaxy that is a reservoir for future star formation? And is there any evidence of maybe passing nearby a larger spiral galaxy that would create a shock to trigger that?
Great question. It's really difficult to be able to estimate what the previous gas content of a galaxy is. Leo P does currently have a gaseous disk, and it's comparable to its gas mass is comparable to its stellar mass. So it explains, why the galaxy is star forming today. That transition between the pause and star formation and reignition, whether or not the galaxy has just been the gas basically photo evaporated through reionization and supernova feedback, or whether it was just heated and extended and just sort of sat there and waited to cool through maybe atomic line cooling processes or something for a very long time, is not really possible to discern with observations. So I don't know the answer to that, but I can say that we did look at whether or not this little galaxy may have had an early flyby with the proto-local group when Andromeda and Milky Way were first forming. There was potentially a long distance kind of flyby interaction. And if that pans out, then that could be one of the reasons, it could be an explanation for the reignition. Some of the follow-up observations we're doing with these extra 4, I mentioned we're doubling the sample. A couple of them are sitting not in sort of the same region as Leo P. And so it would be kind of a smoking gun if all of them showed very similar evidence in the timing of the pauses with Leo P, because then you could think of this little association of dwarf galaxies passing by the Milky Way and Andromeda at early times, sort of in lockstep. So that's a possibility for reionization. Some of the counter arguments against that is that the other 3 galaxies for which we already have the data and are not similarly located like Leo P outside the local group show very similar patterns with similar timing too. And so then you would need some kind of odd coincidence to try and get all of that timing to align. So that's why, the reignition truly is an open question, but you in the previous question touched on many of them. So it could be just the galaxy got to sit in this isolated environment, accrete more dark matter and gas, grow and reignite, after the gas cooled. It could have had a flyby of a proto-local group. So there are a number of different, there's another theory that perhaps it held on to its gas post-reionization, but had some smaller interaction with maybe some diffuse gas in the intergalactic medium that triggered and reignited the star formation. I think our best avenue to sort of disentangle some of the different scenarios is by using an extended sample. And we already have new JWST data coming in on a couple galaxies, as well as some archival Hubble on another galaxy that we're going to be using to work on that.
Hey, this is Liz Landau from NASA. Thank you all so much for your great talks. And my question is for Zhuo, a little bit similar to Jennifer's question. It's such a beautiful mosaic. And I guess I wondered, what is your biggest burning unanswered question about Andromeda that something like this could hint at and more data could help answer?
Yeah, thank you. That's a good question. So I think the big question we always want to know is the merger history of Andromeda. For example, some of the competing models are predicting different scenarios and different signatures on the 2 halves of the disk. For example, if there was a big major merger in the past or several minor mergers in the past. So for the one major merger in the past, they predicted like a 1/2 of the disk showed around like a burst around 2 to 4 gig years old, but the other half does not. So that's the big signature we can definitely compare using our latest 1,500 of observations to extract the star formation history on the south and see if there is such signature compared to the north. And some other stuff going on, for example, the interactions with M32, that's definitely the highlight of this southern half. For example, I think 2 years ago, the amateur astronomers found the oxygen 3 burst near the split portion of the ring of M31 close to M32. So if so how that can, right? If that's arises from the photoionization or the shock due to the passage of M32. So using the observations on the south could definitely help us further constrain such questions on this fantastic second, like southern half of the disk. Thank you.
Hi, I'm Abby Lee from U Chicago. My question's for Catherine. So in addition to, the star formation history, which could help tell you about the progenitors or merger accretion history, I was wondering if you had any plans to get like stellar kinematics for the streams, to try to build up the accretion history.
Yeah, no, we would love to do that. We do have some proposals in the works for follow-up on these various features. And I think this kind of demonstrates the power of these wide field studies to then identify these interesting regions around galaxies to follow up with things like James Webb and other spectroscopic instruments to really understand the minutia of details between them. So this is something that we're definitely working on, and to really understand and model ultimately the kinematics of the system and really understand, what was the progenitor like? Did it have, say, a metallicity gradient like we have seen in small dwarf galaxies that, say, the Milky Way has accreted? So yeah, we're definitely working towards that.
Looks like we've got a couple questions for John online, so we're going to move to those.
I have a question here from freelancer David Chandler for John. Can you sum up the status of current efforts to work with the companies launching large satellite constellations on ways of mitigating their impact on astronomy? How seriously have the companies been working to minimize their impact?
I would say that we have made some strides in this area through direct communications with launching companies, both through AAS and through the IAU, Center for the Protection of Astronomy from Satellite Constellation Interference. And by working directly with the companies, they have been able to test out some mitigation strategies that then we're able to check on. Essentially, we can run observing campaigns from the ground to try to see, if they make a change to the satellite design or the way that a satellite is oriented in its orbit to try to reflect less light, does that produce the desired result? We have had some success on at least the optical and infrared side in that regard. We're not quite where we would like the major players to be, but they continue to try to improve the situation with engineering. I am concerned about, especially in the radio part of the spectrum, that is turning out to be much more difficult to get a handle on, although there's some innovation taking place with some of the companies right now about switching transmitters on and off as they overfly radio astronomy observatories as a way of reducing the interference. And of course, we're still concerned about the bigger issue of space debris and the crowding of orbital space around the Earth, which raises the potential for collisions. So long story short, it's a bit of a mixed bag at present, but there are some encouraging signs.
Great, thank you. I have another question for you. John. This one's from Monica Young at Sky and Telescope. There seems to be a lot of attention on the interference from satellite constellations, but for overall enjoyment and use of the sky, sky glow seems like a bigger and more intractable problem. In your view, have there been significant movements in mitigating light pollution from artificial lights, or are you finding that bundling this together allows for more forward movement?
Monica, I hope that we can get better forward movement by coupling these things together because they bring different constituencies into this conversation. The people that are most interested in the light pollution angle tend to be, of course, the amateur astronomers, casual stargazers, et cetera. Bringing in satellite constellations, there's the space crowd, as it were, people who are enthusiasts about technology. Many of whom have no idea that these potential impacts on the night sky exist. I think it is fair to say that right now, the bigger concern for ground-based astronomy is certainly light pollution by far. And the news on that is not so great, especially in the past decade. We know that artificial light at night emissions have been rising around the world at a fairly alarming rate. We have some successes on sort of the micro level. But at the same time, I'm encouraged by efforts such as in the European Union with its nature restoration law, which is just coming into force. It has a light pollution component that requires EU member states to reduce their light pollution by 2030. We'll see if that is successful. But I think in the end, it has to be the totality of all of these efforts that's eventually leading towards the same goal, I hope, which is the protection of the night sky overall.
Hi, Jeff Faust of Space News. Question for John again. Regarding this new resolution on obtrusive space advertising, are you seeing any sort of specific threats that you want to sort of get out in front of, or is this sort of a preventative measure before any of these get forward? Because as you mentioned, federal law prohibits obtrusive space advertising in the US, and that law has been on the books for like 20, 25 years.
Yes, it dates to the early 1990s, as a matter of fact. And I think we're mostly forward looking at this point. It's not as though we think that anybody is imminently about to do this, but the lure of it is so great that I can't imagine that no one will try. And in particular, the Russian effort that I mentioned in my presentation, where what they want to do is they want to launch these coordinated or formation flying CubeSats that produce basically a logo in the night sky. And the company said, well, you know, we can turn them off when they're flying over observatories, but it's very clear that they wanted to target the advertising mostly to bigger population centers. But their technology demonstration was evidently successful as far as anybody knows. And I think the commercial value of this will prompt somebody to do it. We're in a good situation here in the US because of the existing law, but a company that was really determined to deploy space advertising could simply go to another launching state that doesn't have a law like that on the books, which is why we urge the UN delegation from the United States to go actively promote this issue and try to establish it as at least a norm within the international community to not engage in this form of advertising, using as an example the US statute.
Susanna, Kohler, AAS, following up on that, because I'm curious, how secure do you feel that the US law is, particularly with the incoming administration? Is it something that would be easy to roll back or not?
I don't think it would be especially easy to roll back, but I also don't sense that there's a lot of appetite for that at the moment. Because that law was enacted by Congress, it would be something that required another act of Congress to roll back, formally speaking. Now, the administration could, if it decided simply to not enforce that law, that's another matter. But again, right now, as far as we can tell, there's no appetite for that in the United States, and our concern is mostly in countries that don't have laws like this, that companies that want to launch will just go and find a friendly jurisdiction from which to launch their payloads.
Thank you. Any last questions in the room or online?
In the back.
Hi, Katrina Miller from the New York Times. This question is for John. Does Compass mainly operate in an advisory role for policymakers? Or are there other aspects of the committee? And if so, can you talk a little bit about those?
Yes, that's a good question. We're a purely advisory body, as it were. We formally advise the board of trustees of AAS to take these positions, for example. So that involves pulling together experts on the subject matter, formulating what we think the society position should be, and then it runs up through different layers of review. And if it passes the board of trustees, then it becomes something that would be published on the AAS website. We engage in some advocacy with the AAS Public Policy Office, We mainly support what they are doing. Lots of folks in town in DC this week for the meeting, and so there were many Hill visits that take place. And we do general advocacy as well, not just policy formulation. We have a lot of people that work in their local communities on issues like light pollution. So we try to cover all of these fronts. And if lawmakers, want to come and talk to us about the details of the policy formulation aspect, we are always happy to talk to them.
Great. Thank you so much. So with that, we are going to go ahead and wrap up. We are just past the hour. Thank you again to all of our presenters today. Let's give them another round of applause. And thank you to their PIOs for preparing releases and helping them prepare. All of those will be added to the press kit just as soon as I get around to it. And just to wrap up, thank you for all of you for being here. And let's see if I can bring up the slide. You got it. You know the one, yes. We will see you at the next meeting, which is going to be in Anchorage, Alaska this June. We hope that you will be there or join us online. But we're excited to bring you a press program there as well. Thank you again and have a good rest of the meeting.